coming from the 17 IMUs of the extent suit. Also, external wrench acting on all the links are considered as measurement inputs. In case of the feet links, we get the ground reaction forces from the FT shoes, but we make an assumption here that there is no other external wrench acting on any of the rest of the links on the body, and we set the values, wrench values of this to 0. Now, using the recursive relations, we can define a model constraints equation by rearranging the terms and defining a block diagonal matrix D and a bias vector BD. Similarly, we can construct a measurement equation that maps the dynamic variables and the measurement vector. These two equations can be stacked together to get a linear relationship. And in our consideration, this is an order-determined system that can be solved through weighted pseudo inverse to find the to estimate the variables in the vector D. Alternatively, the variables D and Y can be casted as a stochastic variables with Gaussian distributions, and the estimation problem can be posed as a stochastic estimation problem, where a conditional probability is considered between the variables to estimate, that is D, and the measurement vector Y. Now, a maximum a posteriori estimator tool is considered to find a solution for the dynamic variables here. One of the advantages in this approach is that the ability to enforce the belief in model constraints and the measurement accuracy through a proper choice of covariances. In terms of optimization, the estimator is guided by 3 parts. Prior covariance, which dictates the flexibility in changing the dynamic variables, emphasis on measurement equation enforced by measurements covariance, and emphasis on constraints enforced by model covariance. Now let us quickly examine the effect of changing each of these parameters in estimating the dynamic variables. The prior covariance guides the estimator to change the dynamic variables. Then the measurement covariance guides the estimator to push some of the dynamic variables to be close to their measurements if they are available. Finally, the model covariance guides the estimator to ensure that all the changes in the dynamic variables be consistent with the model constraints. A proper tuning of these 3 covariances will result in a maximum a posteriori solution, which are reasonable estimates for the link and joint dynamic variables that are consistent with the model constraints and the measurement inputs we are giving. Now let us look at a 3D visualization to see the performance of the map estimator in action for the tasks of right foot balancing and left foot balancing. The arrow at the feet reflects the external wrench acting on them. The arrow in yellow color are the wrench measurements that are coming from the force torque shoes. The arrows in blue color reflect the estimates at the feet coming from the map solution. With the covariances of the estimator tuned correctly, we see that the estimates match the measurement. This reflects the accuracy of the estimator in estimating different dynamic variables. Finally, the spears at different human joints reflect the articular stress. This is estimated by projecting the estimated joint wrenches on their motion subspace, and then the spherical joint effort is computed by considering the individual joint torques for the 3 degrees of freedom, which the spherical joint is composed of. Now let us consider a new problem: how to estimate the wrench at the interaction at the hands without any force torque sensors. Consider an example scenario where the human is lifting an object of considerable weight. Under the influence of this object, the ground reaction forces are increased, which is reflected by the increase in the measurements coming from the FT sensors. Looking at the measurement vector, we fill it with the direct measurements coming from the FT shoes for the feet, but for the measurements of the hands, we are setting them to be 0. So the wrench estimates of the hands are pushed close to their measurements, which are 0. The problem of non-collocated wrench estimation deals with estimating the wrench at the hands that reflect the object weight. A possible tuning one would immediately expect to do is considering the measurement covariance at the hands and playing with them. Let's look at the effect of how we can play with the measurement covariances. We can just control that the the estimates at the hands are not pushed towards the measurements, which are set to 0. But at the same time, the estimator has no guidance to push the estimates of the hand wrenches towards the values that reflect the object weight. Furthermore, the estimation of link, axle wrench, and the joint wrench are coupled through the model constraints. So this coupling is this coupling of joint quantities that are intrinsic to the model and link quantities which are independent of the model renders no possibility to influence a change in the hands without affecting the other dynamic variable estimates. So we need to decouple the estimation of external wrench on links and the estimation of internal dynamic variables. Now let's look at the idea of decoupling the link external wrench estimation from internal joint wrench estimation. Centroidal dynamics relate the rate of change of momentum to the net external wrench acting on the system. Here, the inertial frame of reference is indicated here, where the gravity term is pointed in the opposite direction of the inertial frame z-axis. A convenient aspect of the centroidal dynamics is that it is influenced only by the external link wrench, and it is independent from the internal joint wrenches. So we can now relate the rate of change of momentum and sum of all the external wrench acting on 4 links, which we are interested in. That is the feet links and the hand links. Now we can consider a new dynamic variables vector d prime that is composed of just the external link wrench variables instead of the joint variables. Similarly, we consider a new measurement vector that considers only the external link wrench measurements. Also, we consider the rate of change of momentum as a new sensor input to the measurement vector. Using these new variables, we can define a new estimation problem, which is independent from the model constraints. Here, the estimation is guided just by the prior and the measurements. So thanks to this new formulation and the centroidal dynamics, centroidal dynamics as new constraint, this new formulation is decoupled from the decouples the link wrench estimation from the joint wrench estimation. Let us take a look at the effect of covariances in this new formulation. The feet measurement covariances enforce the estimator to push the feet estimates close to their measurements coming from the force torque shoes. Now, as defined before, the hand measurement covariances can be played such that the wrench estimates are not pushed close to 0, which are the measurements we are setting in. And finally, the measurement covariance for the rate of change of momentum enforces the estimator to change the hand wrench estimates to reflect the increase in the feet measurements, which is under the influence of object weight. But let's look at the intuition behind this idea through the central dynamics constraint we are adding. Let's consider the equation which we considered before that considers only the links which we are interested in. That is the feet links and the hand links. The last term here is related to the weight of the subject, that is the human, given the mass of the human. Now consider a static case where the rate of change of momentum is 0. In this case, the estimator reference becomes the estimator reference to adjust the various to adjust the estimates of the hand for the wrench becomes this equation, where in case of object without any weight, the subject weight is reflected in the force torque measurements, and the estimates of the feet are equal to the subject weight. So to balance out the equations, there is no other values to estimate for the left hand and right hand. And the estimator just puts the values of these hand estimates to be 0. Now consider the case when the human is lifting the object. Here, the estimates at the hands, at the feet are subject weight plus the object weight. So in order to balance out the forces and torques, the estimator pushes the hand wrench estimates to reflect the object weight. So revisiting the problem before, previously we were estimating the link wrench estimates at the hands to be 0, but now thanks to this new formulation and consideration of centroidal dynamics, we can push the estimates at the hands to reflect the object weight without having any sensors. Now let's look at the small video where the human is performing the lifting of an object, and you can see the non-collocated wrench estimation that reflects the weight of the object at the hands. That concludes the first part related to holistic human perception. Now let's look at the second part that deals with reactive robot control. This part is divided into partner-aware control, where we consider a coupled formalism for a typical physical human-robot collaboration scenario. And then we explore the ideas of interaction, helpful interaction, and interaction exploitation towards designing a new partner-aware controllers. The second part is related to trajectory advancement, which deals with the concept of collaborative behaviors when the robot is getting an assistance from a human. This figure indicates a typical physical human-robot collaboration scenario where we have the three main components. That is the human, the robot, and the environment. Also, this figure highlights the different contact locations that are involved between any of the agents, between the human and the robot, and the agents and the environment. Thanks to the consideration of our human model as a rigid multi-body mechanical system, we can now consider the equations of motion of both the human and the robot together as a combined system. Coming to the kinematic constraints, the constraints that are involved with the links that are in contact with the environment can be posed as the link velocities to be 0. And the mutual contacts between the robot and the human can be posed as links that have the same velocity. Now, these combined equations of motion, along with the contact constraints, can be considered together to get a function of the interaction range, which is a function of the joint torques of the human, the robot, the system configuration, and system velocity of both the human and the robot. An interesting quantity here is the human joint torques. These are independent of the robot, and they are largely self-generated and self-regulated by the human. It would be very interesting to characterize the interaction in terms of joint torques and then exploit them to design controllers. For example, it would be nice to have a controller for the robot that will optimize the ergonomy based on the human joint torques. But before going to the idea of exploiting, let's define the questions of how we define helpful interaction and then how we define interaction exploitation. To explore the idea of helpful interaction, let's consider a simple toy problem where we have an object of negligible mass. There is a control input on this object, and there is an external force applied to the object. The equations of motion of this simple system relates the acceleration to the control input and the external force on the object. Let's consider a simple task where we want to control this object to go along a desired trajectory, and we can come up with a simple control objective like this. Now, what we are interested in this, in the idea of helpful interaction, is to see how we can characterize the external force that we are that's affecting the object can be characterized as a helpful interaction. This problem can be investigated through the stability analysis from Lyapunov theory. Let's consider a simple Lyapunov analysis, Lyapunov function, which on taking time derivative, we get a relation in which we can use the acceleration from the equations of motion and then simplify it to expressions involving control inputs and the external force. Given the task of trajectory tracking, we can use this desired dynamics control input and simplify this equation further. Now, the stability of the system under the influence of this control input, and more importantly, this external force, is ensured only when the Lyapunov function, a derivative of the Lyapunov function, is negative. The second term here is always negative. Now, the stability is decided based on how the first term behaves. As long as this first term is negative, the interaction force here can be characterized as a helpful interaction force. Now, let us look at this idea through another intuitive example. Let's consider a case where the current velocity is lagging behind the desired velocity. In this case, the velocity error is negative. Now, an interaction force that is applied on the current velocity, which pushes it towards the desired velocity, is in the positive direction. And this can be characterized as a helpful interaction because the first term of the Lyapunov function becomes negative. Similarly, let's look at another situation where the current velocity is leading the desired velocity, and an interaction force applied in the negative direction, which pushes the current velocity towards the desired, is characterized as helpful interaction. Now, with this idea of helpful interaction definition, let's build the idea of interaction exploitation. For this, let's consider a simple Cartesian trajectory tracking problem for the end effector of the robot. Let's say you want to control the hand of the robot. The equations of motion of a floating waste mechanical system can be defined by this relation, where we have an external interaction wrench acting at the hands at the end effector, let's say. From this relation, we can find the system accelerations equation. And then we also have the end effector velocity mapped through Jacobian to the system velocity, which on taking time derivative, we can get the relation for the end effector acceleration. By combining these two acceleration equations, we can get a relation for the feedback linearized robot control torques. An important point to observe in the behavior of this feedback linearized robot control torques is that they are completely agnostic to the external wrench. So any external interaction wrench that a human tries to apply is completely compensated by the control torques that are generated through this feedback linearization approach. But we would like to, now let's build on the idea of what we were looking before, which constitutes a helpful interaction force by considering the Lebnow function. By doing a similar analysis, in this case for a robot, we get at the derivative of the we get the relation for the derivative of the Lebnow function in this way, where there are terms included for the Jacobian too. Similar to before, let's do a simple wrench decomposition of as before, as long as this second term is negative, the interaction wrench here can be characterized as a helpful interaction wrench. To look at how we can let's do a simple decomposition of this interaction wrench along the parallel and perpendicular directions for the velocity error. Now, the term that is relevant to the velocities is the term which is in parallel, in the parallel direction for the velocity error, that is alpha. As long as this term alpha is negative, we can be sure that the system is stable under the influence of this external wrench because the derivative of the Lebnow function becomes negative. But how we can exploit this is by updating desired dynamics for the system based on the value of alpha. That is, when the alpha value is positive, we can completely compensate this interaction wrench because they are not helpful at all. So we are fine with the feedback linearized robot control torques. But when the value of alpha is negative, we can actually use this information as a desired dynamics and then update our and the robot control torques will not compensate for this particular component of helpful interaction. This kind of preliminary investigations are carried in a previous work where the interaction wrench at the hands of the robot are considered towards helpful interaction exploitation. One of the limitations in these works is that the interaction wrench at the hands is not available directly through sensor measurements by embedding force torque sensors at the hands of the ICAP robot. They are actually an estimation from the function of the robot torques. So this forms an algebraic loop that was not convenient. Furthermore, in a couple dynamic modeling, for a physical human-robot collaboration scenario, this is not ideal because the robot control torques are related to the interaction wrenches which we are estimating. These limitations motivated us to consider the new approach, which is the current investigation of partner-aware control, where the interaction is characterized in terms of human joint torques, and the ideas of interaction exploitation is implemented in terms of human joint torques. Now, a partner-aware control law is proposed based on the ideas we saw before, where with a whole body controller that is designed to make the ICAP robot, humanoid robot, perform the stand-up task. The stand-up controller is basically a momentum-based controller with the high priority given with the pre-designed center of mass time trajectory. The state mission of the controller is divided into 4 states, where in the first state, the robot is balancing on the chair and it reaches state 2 by moving the center of mass forward. Then it reaches state 3 by moving the center of mass a little higher. And it reaches state 4 by moving the center of mass further forward and higher. During states 1 and 2, the upper legs of the robot are in contact with the environment, which is the chair. During states 2 and 3, the feet are in contact with the environment, which is the ground. Now, the actual experiments which we consider is this way, where the human is in a completely sensorized suit that gives the information of human in terms of using our holistic human perception framework. But at the time of these experiments, we had a limitation on the system, and the system was not ready yet. So we performed experiments with 2 humanoid robots. Thanks to the modeling consideration of human as a rigid body rigid multi-body system, we can consider other human in place of other robot in place of a human. Here, the purple robot is partner-aware controlled in torque mode, and the green robot, which substitutes for the human, executes a predefined joint trajectory in position control mode. Ideally, this experiment was not easy to realize because the hands of the ICAP robot are very fragile to have any sustained power grasps for long duration experiments. But thanks to our ICAP tech team, we designed new mechanical rigid couplings and attached them at the wrist of the hands, to which we link another mechanical linkages, and then connect two hands of the robot together to get a rigid coupling. This is the experiment of Standup Controller, where the green robot is actually helping the purple robot to stand up. The purple robot is in torque control mode, whereas the green robot is performing the predefined joint trajectories in position control mode. Now, at this point, some interesting questions about the behavior of the robot can be asked. What happens if the interaction is constant towards one direction strongly? The robot still moves at the same predefined velocity, that is, and the reference trajectory is not influenced at all by the interaction the human is having towards. But a collaborative behavior, which one would expect, is that the robot updates the reference velocity and moves along faster based on the interaction wrench that the human is providing. This is the motivation behind the concept of trajectory advancement. For example, consider a scenario where you have a manipulator robot that is trying to perform a pick and place task. When the manipulator robot is moving down, a human with the intention to actually assist the robot can hold the end effector and pull it down. In this case, instead of the robot being compliant and losing the accuracy of the task, it can actually go along the predefined trajectory, but advance along the trajectory using the interaction wrench that the human is providing. So the problem statement can be summarized as, given a task of reference trajectory tracking, how can a robot advance along the trajectory by leveraging assistance from the intentional physical interactions the human is providing? So normal behavior here can be characterized as by looking at these two timestamps. These are the position of the current velocities. The position of the velocities in these two timestamps in a normal behavior are shown here. But the updated reference velocity concept, which is trajectory advancement, shows that at the time instant 0, when an external wrench is applied if that is a helpful interaction wrench, the robot can actually get an updated reference for the timestamp at the next timestamp. This approach involves 3 steps where we parameterize the reference trajectory. Typically, the trajectories are time parameterized. Instead of that, we parameterize, we consider a new parameter called pre-parameter that is independent of time. I'll explain the choice of this parameter shortly. Now, the reference trajectory in the new parameterization is given by this set of equations. Now, coming to the interaction exploitation for the reference with the task of trajectory tracking, previously we were decomposing the wrench along the velocity error. Now we decompose the wrench along the direction of the current desired velocity. And this term is considered to be a correction wrench, which is a bit of a misnomer, but it's more of an intuitive name. So whenever the value of alpha is positive, it means that the interaction wrench is in the direction of the current desired velocity. In this case, we perform a Lyapunov analysis to arrive at an update rule for the trajectory advancement. This is the update rule for the trajectory advancement, where this indicates the rate of advancement along the trajectory that depends on the measure for the trajectory advancement, which depends on the value of interaction wrench. The value here, the value 1 here highlights that this trajectory advancement is similar. The new trajectory which we are parameterizing in the free parameter is similar to the time parameter's trajectory, and the value, this value is the upper limit on the amount of trajectory advancement, just to ensure the safe interaction with the human. These ideas are tested with a simple and effective trajectory tracking controller, and the task is for the right foot of the robot to track a predefined Cartesian trajectory that is parameterized in the free parameter. At this point, we can consider simple interaction wrenches in simulation, where if the direction of motion is along the positive x direction, and if there exists an interaction wrench in this direction, then that interaction wrench can be categorized as assistive wrench. Any other wrench which does not have any interaction wrench in the direction of motion is considered to be agnostic, that does not have any effect of trajectory advancement. This shows the video of simulation results where when the desired direction of motion is in the positive x direction and we apply an external interaction wrench, you can see there is a correction term that reflects the interaction wrench, which results in trajectory advancement by increasing the rate of advancement for the parameter psi. That can be integrated to find the next position for the parameter to give an updated reference, which indicates the amount of advancement we can go along the trajectory. Now, these interaction wrenches are are categorized as agnostic wrenches, which are not in the direction of motion, so they do not have any trajectory advancement influence. We also tested this trajectory advancement concept on a real robot. Now, when the robot is moving in the forward direction and an interaction wrench is applied, when the robot is moving in the backward direction and an interaction wrench is applied in this direction, that is categorized as a correction wrench, and the trajectory advancement is considered by updating the free parameter. In these directions, the robot is agnostic to the interaction wrench, and the trajectory advancement is inactive. Finally, we also updated the Standup Controller with the idea of trajectory advancement and performed some tests in simulation, where during the entire duration of standing, we applied constant wrenches at the hands of the robot. This shows the different instances when the robot is performing the stand-up tasks. Here you can see in simulation we are applying interaction wrenches at the hands when the robot is standing, and you can see the robot standing under the influence of interaction wrench. Now let's look at the results to see how the concept of trajectory advancement is actually working out. Here in the figure you can see a quick jump in the trajectory for x, y, and z directions at the instances where the interaction wrench is applied, and those interaction wrenches are helpful towards trajectory advancement. The trajectory which is smooth here is the original trajectory without the concept of trajectory advancement. These results are also verified on the real robot, where you can see quick transitions with the concept of trajectory advancement on, and without the concept of trajectory advancement, there are smooth trajectories which are normal behavior of the robot. So to conclude, I worked on these ideas of holistic human perception, mainly related to kinematics and the dynamics of the human side. And on the partner-aware reactive control side, I worked on integration of human quantities and the characterization and exploitation of interaction wrench, and then finally some collaborative robot behavior during physical human-robot collaboration scenarios. Coming to the open challenges, I haven't investigated anything related to psychological, physiological signals because it's not relevant in physical and human-robot collaboration scenarios, which I was aiming at. Further, in our case, the human model is based on an anthropomorphic reference table, which is kind of really an old school approach in designing a human model. More recently, body segment inertial parameter identification is becoming popular as it is kind of independent from any constraints and can be applied to broader range of demographics. Also, the inverse kinematics is not aligned really with the estimation of the dynamics, where we can use the concept of dynamically consistent inverse kinematics to correct any inaccuracies in the inverse kinematics. Further, the covariance tuning for the choice of different covariances is right now done manually, and it could be interesting to see if we can perform any dynamic covariance tuning. And lastly, there is no prediction step involved in our human motion, in our human holistic human perception framework. Coming onto the robot control side, we do not do any predictive robot control at this stage. Also, ergonomy optimization is not performed on the controller side to help the human. And to conclude, there is no higher level task planning for this system. And it would be interesting to see how these concepts of holistic human perception can be integrated for a higher level task planning where the human and robot are sharing a scenario together. I think that's it. Thank you.
Okay. So I believe that now we can start with the Rashid is the only reviewer. So Rashid, you can start the question time.
Okay, so I've seen in the document that there is also Dana Kulic, but she's not here, I think. I assume, yeah.
No, Dana is not
so
here.
I will start. Yeah.
Yes.
I will start. So I was very pleased to hear this talk, and I've read, of course, the document and reported on it, and I like it. It's very interesting and very serious work. With a number of interesting questions discussed and contributions. Since it is very well, and it makes me think a lot, and I can discuss a lot about it, but I will not do it because to save time and because it is quite late. It's already 7:10. So, but still, I will ask 2 or 3, or perhaps 4 questions. But I will ask you also, Kashef, to please to answer shortly,
sure.
So that we do not kill the audience. The first thing is that, again, I said I like it. I will go through different steps. First, I would like to discuss a little with you I would say the first slide, the architecture that you propose.
Yep.
Let's look to the slide 6, I think. I think it was.
Can you see the screen?
No, the screen is from my side is void. I don't know why. I have seen these slides before, but not now.
Just a second. No?
Not yet.
Good for me.
Yes, good for me.
Yeah, it takes time sometimes to come. Okay. But I have your slides, so I can see the PowerPoint.
Okay.
It's coming. It's coming. Now I have it too. Yeah. So in this scheme, so this is the kind of architecture you discuss the issue of HRI, HRC, and essentially human intent. In fact, in what you are drawing here, and in fact in what you will see afterwards in your talk, you mentioned the human intent here entering the planner.
Mm-hmm.
But there are 2 levels, I would say, of human intent. Okay, there is the human intent which corresponds to the global, to the task. What does he want the robot to do, or what do they want to do? And the second level of human intent, which is more local, I would say, which is I would say the assistance or disturbance of the robot while it is doing its task, and the adaptation of the human in it. So is this also going to the planner, or is it integrated fully in your feedback?
Right now, I don't have any planner included with the human intent information. This was more like a representation of the state of the art, where we can actually use a planner to update the references for the target, for the robot, based on the human intent. This is just as a reference template of the state of the art.
Okay, so in your scheme for the moment, you are essentially using the human intent in the feedback, I would say.
The main goal is this slide, where the human information coming through the model considered as URDF is actually considered to formulate the reactive robot control side. So I'm not actually using any planners at the moment to update any references for the robot.
Yeah,
but the main goal is
I understand.
Yeah. Sorry, I think I did not get the question right.
Yeah, I mean, in your general scheme, where the how would say, the action of the human is taken into account in your architecture? Is it taken into account in the feedback for the robot controller only, or part of it is going there and part of it is going in as human intent, higher level?
There is no other
it seems to me that okay.
Yeah, that's one of the
so
limitations at the moment.
Okay. So we'll discuss about this in the, I would say, third question. I'm coming to it. Second, just a small question. In the example that you are showing, where you do the weight estimation based on the kinematic, dynamic system, etc. So you show a system, and you show that you are able to estimate the weight of the object. At which accuracy are you able to do this? How much this is dependent of the strength of the human? How do you calibrate this?
At the moment,
how could you calibrate this?
At the moment, I would say this is more like a qualitative output rather than a quantitative output. Basically, this estimation is guided by how we are changing these two variables. The first one is the covariance that's related to the measurements. If I'm making these covariances very tight, what we do is to push these estimates close to the measurements, which are 0. But if we make this covariance on the rate of change of momentum high, we actually push the estimates of the hands close to the object weight. So this is kind of like an intuitive tuning rather than any pre-designed tuning at the moment. So we get qualitative results. And the tuning we would do is we take a predefined weight, let's say 5 kgs or 10 kgs at the hand, and then try to tune the covariances so that the estimates reflect the weights we are lifting.
Okay. But can you adapt this from one human to another? I mean, if you know the human.
Sorry, I did not get the question.
I mean, if the robot knows precisely the human and his strength, can he adapt this to have a quite sufficiently good estimate?
The idea is basically this, where we can actually use the information estimated in this way, the hands, rather than the information coming from the hands of the robot for stock information, because those are the estimates that are directly coupled with the robot joint torques. So if we can perform a good tuning, we can actually get this information from the hands when the human is interacting with the robot too.
Okay. Now I'll move to another thing. So I like very much your scheme where you define this notion of helpful interaction force, and how you develop a scheme where the robot could then there is a second notion which is complementary to it, that you call it the trajectory advancement.
Yes.
Okay. Which means somehow the information comes to the robot in order not to change its plan, but to adapt its task, what it is doing. Yeah.
Yes. It's not like a planner directed updated reference, but basically you're changing the.
I say when I mean the plan, I mean there is a task running already.
Yes.
Okay.
Yes.
The robot is already performing a task. Okay.
Yes.
Which has been planned somehow or programmed. okay? And then the trajectory advancement comes here to help if the robot is correctly equipped, the robot to perform its task. Of course, if the robot is agnostic of this, it will compensate and not take benefit. Okay.
Yes.
If it uses your scheme, it can take benefit of this trajectory advancement. Yeah. Okay.
Yes.
So this I think this is very interesting, as I mentioned, and this make me think. So I will ask you here. So I like it. I find it very, very interesting, and you are showing very, very interesting result about it.
Thank you.
But still, there are a number of questions that come here, which are because you are using it in a way where what happens, for example. So I'm pushing you a little to something. What happens if when the human is helping, okay, it makes the system go too fast for the perception action loop of the robot?
I don't think there is any perception loop involved. Well, okay, the perception loop is basically the interaction wrenches.
I understand.
Which are coming from the hand.
Exactly, but let's assume you have a task where there is a perception. For example, the robot is trying to put an object in a pegging hole, somewhere. Okay.
Yeah. Yeah.
And the human helps him. Okay.
Yeah. Yeah.
But so you could say, since the human is helping, the robot will perhaps go faster. Okay.
Yeah.
But then it is perhaps too fast for its perception because the robot is tracking with perception where the hole.
Okay.
Okay.
Okay. Okay. Well, this concept is more designed. Definitely, there will be a problem in such a situation, because this concept is designed in a way that we define a trajectory that is parameterized in a new parameter, and the design choice for this trajectory is more important. If you are actually updating this trajectory based on perception system like vision, it's definitely not going to work directly.
Why not? Perhaps it could work. The robot should have to balance this. I'm pushing you to this, essentially. I think it's interesting questions, okay? How much I can exploit, me the robot, and how much I cannot exploit because it's going too fast, for example. But I give you another example. If the robot is confident on the human perception, then it could accept to go fast. Okay.
Yes.
This is what happens to us. If you close your eyes and someone has it helping you, if you trust the person, you can accept to go faster. Okay. Somehow, I mean, to rely on his own perception action loop. Okay. This is what I'm pushing to you. My question is: do you think your scheme could be extended to the fact that there is not one action but two perception action loops running in parallel, one of the human and one of the robot? Okay.
Yes.
And because this could be exploited in two ways: helping, okay, and relying on the human, but also it could be used from the other side. Okay. For example, if the human slows down or pushes the robot in one direction or another, what should the robot do? Okay, depending on the situation, it could accept or compensate.
Okay.
Okay, it is accepted as helping. What I mean is that what seems not positive in terms of advancing in the task could be good. You see, so this is essentially my question. Okay, how can you integrate this in an extension of your system?
I can actually think of this trajectory advancement as like a repertoire of behaviors next to the compliant interaction behaviors. So you can actually, you can switch between these behaviors based on, let's say, some metrics on how reliant you can actually configure your system based on the human perception. If you're confident
Yeah,
on the human
and
perception, yes.
Exactly. So yeah, so this is essentially my point that I wanted to say to
Okay.
you. I
Okay.
like it, and I find it very interesting, and I will think about it and discuss about it. But I think it has to be mitigated with other aspects
Yes.
linked to why the human is acting this way or this way.
Definitely.
Essentially. But another aspect that could be taken into account is that the robot could also exploit, perhaps to go faster. Let's say, how can you adapt this, for example?
Sorry, I lost you there.
I mean, the robot could exploit this trajectory advancement, perhaps, or force exerted to reduce its own energy consumption instead of going faster. Okay. How can you play on this parameter, for example? Okay. It's like when someone helps you, you reduce the consumption of your own energy. It's help. Okay. But you do not go. You do not go faster. Okay.
Okay.
And you do this by reducing the energy. The force you're exerting yourself.
Sorry, I didn't get it.
For example, when the human helps the robot, okay, and the robot perceives this helpful interaction force, okay, it can exploit it in two ways. One is allowing the task to go faster, okay, to converge faster, or simply reducing its own contribution to it.
Yes.
How do you balance this?
You can design the controller to actually, let's say, reduce certain joint torques. You can reduce. You can aim at reducing joint torques. For example, in the stand-up task, you can use this interaction and then actually ask the robot to apply less joint torques at the knees when the interaction is helpful.
Yeah. I would say that in this case, the robot will be more cautious somehow.
Yes.
It will
save
energy.
It's more like a conservative approach.
Exactly. Exactly. Okay. So I propose to stop here. I'm happy for this, and it's interesting. And I give again
Thank
to
you
the
very
floor.
much.
Okay. Thank you.
Okay. Thank you very much, Rashid. So we move to Antonio.
Can you hear me?
Yes. Hello.
Thanks a lot for the presentation. A very interesting topic.
Thank you.
I was wondering whether you are familiar with the concept of passivity for dynamical systems. Have you ever heard of it?
I'm not strong at it, but yes.
So if you remember a bit what passivity is, can you maybe think about the relations between, let's say, a passive interconnection and the helpful interaction that you sketched? I kind of see many similarities, or passive behavior of this external system and the helpful interaction.
At the moment, I cannot really give a good answer, I'm afraid.
Okay, because I think so. Then I suggest you to have a look to it. I think for the sake of sparing some time, I'm not going on this question, but I think there is some interesting relation with it. So I suggest you to have a look with it.
Okay.
So you're welcome. At slide 41, I think it was, there is a yes, there is one robot that is in interaction control mode, and the other one is in position, right? Control.
Yes.
So maybe I missed it, but why they are not both in interaction control mode, and what would happen if they?
Because the idea here is to actually replicate the experiment of this form, where we consider the human system that is providing all the human quantities in terms of like a mathematically similar way for the controller. But at the time of the experiments, we did not have any system for the human in place ready to get all this information for the controller. So we replaced with another human, which is executing a predefined trajectory for it. But if you're trying to execute like any trajectory in this coupled dynamics formulation for the control torques for the robot which is assisting, it'll actually create loops, control loops, if we are using the joint torques of this robot. So this is in this investigation considers just the joint torques of the human, expressed in the form of this new robot which replaces for the human, which is not optimized by the global control law for the combined system.
Okay,
Because
and what do you think it would happen if both were controlled at the level? So would this work?
This won't work in this modeling because we didn't model for a situation like this for this controller. But there is a current investigation which one of our colleagues is working for like collaborative robot-robot controllers, where we optimize, where we try to generate control torques for both the robots together by considering the combined system together. At the moment, I didn't do any work related to that yet, but there is an investigation going on by another colleague.
Okay, and then last question I have. What if, so instead of controlling directly the range, you do like, I think maybe maybe Gabriele or also the others, the other two presentation today, they in some parts they presented the jerk level control with where the force is put into the state. Okay, so you can, for example, define a certain force reference and look at whether the external force is following or not the force reference, include this in the error, in the state error, and then by controlling as input the derivative of the input range, would that result in an automatic, let's say, exploitation of the external perceived range when it's an helpful interaction or when it goes in the right direction? Would be something that let's say is equivalent to what is done in the helpful interaction paradigm, or would be something?
But I cannot understand the relation from the jerk controller side with respect to the interaction exploitation, because the limitation which was done before was that there is a direct relation between the force torques at the hands, which are estimated but not measured through the sensors.
What I meant is that in order to understand whether a force goes in the right direction, let's say, or not, or is impeding the desired motion, what you compare is the force with the, let's say, the trajectory. You project it on the trajectory. You check whether it's in the direction of the desired velocity, let's say. With this, you can discriminate whether it goes in favor of the motion or not. And then I think there is a part in which you also speed up or slow down the trajectory, along the trajectory with this parameter. You change the time law, if I understand.
Yes.
So would it work instead? So would it work instead to make it in a different way? So to know which are the forces, to put the forces in the state space, and to define an error at the level of forces. And then controlling the derivative of the input force with, for example, a proportional controller where the force, the error, a component proportional to the force error is present. Would that be another way to also try to implicitly include the external force in the loop and let's say cope if it's going against the motion, the desired task, or exploit it if it's going in the direction of the desired task?
I cannot really think of that, because right now it's kind of only using a parameterized trajectory, which is not considering any forces that are coming from the robot. It's kind of independent at the moment. But
In
considering
that
them
case,
together,
the parameterized trajectory should include the forces.
yeah,
somehow.
somehow include the forces and also kind of estimate this interaction range to be aligned with the consideration of the forces coming from the robot too.
Okay, so these were my three only questions. I leave the floor to the next member. Thank you very much.
Okay, so the next one is Robert.
Okay, great. So this is a little outside of my area of expertise, so you'll have to forgive me for not having very necessarily interesting questions. One of the things that I was a little curious about is, really early on you showed that this dynamical optimization strategy is both the fastest strategy by a long shot and also the most accurate. And I was kind of wondering if you could expand on what you think it is that caused the quantitative results of that approach to be so much more accurate than the other approaches.
I'm not really confident to explain it in detail, but basically this is kind of like based on the control theory, where you use the control references as basically the post targets and velocity targets, which are our reference inputs. And another interesting observation was the consideration of orientation in terms of rotation parameterization was an important factor to make this dynamical optimization much faster. Other than that, I'm not really sure of all these details because this implementation was not primarily done by me.
Okay. My only other real question then is related to the trajectory advancement stuff, which seems to be a common theme. Everyone's pretty interested in that. So it basically looks at the current state and uses that as a way of modifying the rate at which time passes. Is that correct?
Yeah.
Okay. So my question is, what would happen if it was required to have like a discrete jump in the actual signal? So, or if the best option was to have a discrete jump. And so my thought there is, if I have a error in the positive direction of time, but then my actual trajectory, the slope of it right now, would have me moving in the negative direction. So then if I understand correctly what's happening, you would actually just increase the rate at which you're advancing in the negative direction so that you can quickly go positive. Is that right?
Exactly. That's how it behaves at the moment.
Okay. What do you think it would take to have it kind of not necessarily have to go in the negative direction, because you're going to induce additional error before you can start correcting?
Basically, we can look at the limits of a trajectory, and then see if there is going to be a direction reversal with respect to the instant. With respect to the direction in which at the current instant we are considering the range to be helpful. If there is going to be a future change there, then we can stop this concept of trajectory advancement and fall back to normal behavior. So you wouldn't have this sudden jump going from a forward direction back to the reverse direction.
Okay. And other than that, I really enjoyed it. Thought it was a great presentation, and thank you very much.
Thank you very much.
Okay, so I think that now is the turn of Ludovic.
Yes. Hi. So yeah, thank you very much for the very interesting presentation. I thought it was really good.
Thank you.
It's also a little bit out of what I usually know, but I really enjoyed it. I had a few questions concerning the estimation part.
Yes, sure.
I was wondering how much of your how much is it dependent on you, especially when you start to basically estimate branches, right?
Yeah.
How much is it dependent on on having a good dynamical model? And I assume that it's not that straightforward to get for humans, right?
It's kind of again, here we have like an overdetermined system because we consider a lot of constraints in place. we have this 17 initial measurement units which we're considering, and we also consider link on all the ranges. So basically the trick is to kind of tune this measurement covariances on these sensor inputs, which are kind of our reference for the estimates. We get a behavior where we check if the measured range and the estimated range to which we can compare to is kind of aligned. This is kind of like the way we are doing the tuning at the moment.
Okay. And so when you did the estimation, as far as I understand, if I remember correctly, do you get unbiased estimation, assuming that you have a zero mean disturbances, right? Which
Yeah.
I guess, I don't know if you need Gaussian or you just need finite variance in this case, but either way.
Yeah.
I assume in your case this is not true, right? Because you have errors in your so your measurement error shows up in more than just the forces, right? And in forces you can have biases as well. So do you know if it influences a lot the results that you actually get?
I did not get the question precisely.
So the MAP estimator works assuming that you have a zero variance noise and basically Gaussian distribution, right?
Yes.
This is not true in reality. And in particular, you have nonlinearities in your model where you basically some of the if I understood correctly, some of your measurements shows up or go into the nonlinearity, right? Even if it's not what you try to estimate.
Yes.
So this basically creates potentially nonlinear effects that potentially you have not only Gaussian, you don't have Gaussian distributions anymore, but you might have multimodal distributions. So this might create biases in your estimations or basically wrong estimation. And I was wondering how in practice is actually what happens in practice is really an issue or not.
One thing is we are not really confident about the joint torque estimation we are doing to say like they're precisely what one would expect from rigid body modeling because we didn't do any benchmarking for that. So maybe looking at the joint torque estimates, we can check more about what you're stating. As far as the current approach, we are just trying to align the measurements for the feet ranges, which we are confident about, to match the estimates of the feet ranges. And also we are matching the measurements from the accelerometers to the linked linear accelerations. So there could be a problem in the estimates for other variables which we cannot directly measure and compare. But at the moment, I'm not really confident to say which ones are not being estimated correctly.
Okay. So do you think you could design a procedure that would be able to quantify this maybe more precisely because I guess you want to use that in production somehow, right? At some point.
Yes, at some point, yeah. Another thing also we recently considered was to see the accuracy of our IK because we are not really benchmarking our IK at the accuracy level. That could also propagate some errors when we are doing this estimation because we are giving that information as a model constraints that's related to the model constraints. So the idea is to do like a dynamically consistent inverse kinematics and then update the IK, improve the IK accuracy, and then feed it back to the estimation for the dynamics.
Okay, that's great. I have a question on the other part. When you do basically the trajectory advancement, that's maybe something I did not understand very well. So when you basically move forward on the trajectory, the problem of when I'm doing time reparametrization, right, of the trajectory is that you might be able to violate a lot of dynamical constraints. And it was not clear to me if you and how you basically handle that. You see what I mean? So you might have a lot of dynamic constraints that cannot be satisfied if you do time adaptation so easily.
Yes.
Yeah.
I haven't thought about that because the idea here was to just investigate how a collaborative behavior can be demonstrated. But definitely there is this violation of where you can have the trajectory erratic when it's the direction of polarity reversal in the direction. I haven't thought about that, to be frank.
Okay, that might be interesting. So I think it's very interesting to look into that. I liked the idea, so it might be worth pushing in this direction.
Okay.
Yeah, maybe finally this question is more a bigger question. Is basically, so you said the glass is almost full. So
Yes.
what's next? So what would you do now if you were had the opportunity? You have an additional 2 years or something, do a postdoc. What would be the important questions you would try to address?
First thing would be see how we can improve the estimates for those quantities which are internal, that is the joint dynamic, joint range, and see if our estimates for the joint torques are kind of really benchmarkable with respect to rigid body model that's kind of deterministic. That's the first step to do, and also improve the estimation of this non-collocated range estimation. And then on top of that, try to see if we can do the same estimation in a physical human-robot collaboration scenario, where we typically use interaction forces and torques coming from the robot measurements, but we want to see this non-collocated range estimation in action in a scenario like that, and then use that information for designing the controllers. Another interesting thing we want to do is kind of get away from how we are developing our model based on the anthropomorphic tables. It would be interesting to see actually a body segment inertial parameter identification, and also consider muscle models together. A bigger goal I would really think is kind of having a digital human modeling suite, where our human model is not just for URDF, but also you can also consider biomechanical models for the muscles, and then provide and then do interesting investigations on kind of ergonomy optimization for the human too. Well, there is also prediction part, which one of our European partners are already doing it. Hopefully we'll get some more insights from the prediction side, which we can use for like predictive robot control.
All right, that's it. I don't have any more questions. Thank you very much.
Thank you.
Okay, so Olivier, last one.
Yes, so thank you very much. I also enjoyed very well the presentation.
Thank you.
Also, it's a bit out of my field, I would say, in terms of interaction with human, but I really enjoyed the estimation of human. I think for having a robot interacting with human, it's something interesting. And I really like also the fact that you are in a lab where you can have two humanoid robots interacting with each other.
That's kind of a luxury for sure. I have to agree.
Yes, this is. But I see also that as an opportunity in the sense that you could have I mean, as far as I know the work in the team of Daniele, I think there was a lot of work in estimating the dynamical parameters of the robot itself. Mm-hmm. So I was wondering if at some point you guys envision trying to use your system, but putting the robot in place of the human. Just to check if you're able to, how far you are from the identification that you have done with other means.
Yeah, concerning the benchmarking of human joint torques, one interesting way is exactly what you are proposing, where in place of a human model, we actually use our robot model and then benchmark them against the joint torque estimates we are doing currently on the robot. That is another way we can actually see if our estimation, the map estimator, is giving any erratic behavior, as Professor Ludwig was pointing. I mean, it's kind of like heavy integration work, I would say. There are bits and pieces everywhere. It's just like picking up and putting them in the right way. That takes time sometimes.
Yeah, sure. I mean, I totally agree with that. And just as a small call for everyone, I don't believe that there is so much toolbox for parameter identification, even for robots working well or easily used. I think it's still so. Maybe the theory is here, but the tools to do that are still, I think, usually extremely time-consuming. So anyway. So I think it's nice to go into this direction and to be large and used. And so my second question, and it's going to be the last. So again, going to the axis of the luxury of having two humanoid robots, and I think it's something which has been maybe somehow asked before, but from a pure robotics viewpoint, there are some people like Abderrahman Kedar who propose to such that you switch between an active and passive role. And to me, it looked like here you have a predefined, so the green robot is being the active robot at the predefined joint trajectory level. And for you, how your research work could go into the direction of exploiting this this interaction between active and passive system in order to have the execution of interesting behavior between the two robots?
This work I would consider as more like a proof of concept work, but to truly realize a coupled modeling of two humanoid robots or human and humanoid robot, let's say two humanoid robots, it would be more ideal to consider a global level of torque generation for both the robots. This one is kind of limited in that approach because we are actually leveraging these joint torques as an external signal which guides us for the partner aware control, let's say. For like the true spirit of robot-robot collaboration, that is physical robot-robot collaboration, it would be more ideal to perform like a global level of planning by considering both the systems together, and then and then switching between these behaviors of one being active, which takes the role of leader, and the other one is passive. That's kind of like an investigation which is ongoing at the moment, but with respect to, let's say, optimization of human joint torques in kind of sense for like ergonomy optimization in a balancing task where the human is balancing board along with the robot. You can also replace in that investigation with another robot and kind of like perform like small, let's say, motion for the board where one robot is leading and the other robot is follower for that.
And you think you would have the computational power to tackle the problems with the both together?
Computational power doing in simulation is definitely kind of tricky, but the problem with the real life is kind of it's super messy to perform experiment with these two robots. It's kind of like they're definitely not designed for this purpose, particularly hands of it. So both of them have their problems. In simulation, definitely the computation power is kind of crazy to run like a simulation like that for gazebo, let's say.
I totally agree that you should get rid of them. Yeah, that's for sure. Good point.
Yeah.
Okay, thank you very much.
Thank you.
Yes, so thank you everyone for the long-standing review. We are now, we should quickly basically fill the documents for the commission, which should be really quick. So I kindly ask Stefano, Yeshi, and Gabriele to leave the room.
Yes.
And possibly come back when we tell you. So I'll send you a message. So keep online.
Okay. Thank you, Danny.
Okay. Thank you. See you later.
Thank you, everyone. See you later.
Thank you.
Okay. I think that they left. So once again, I really want to thank you all, guys. It's been it's been really long, and I have to tell you the truth that also we are learning how to do these things online